Hi everyone, myself Dr. C. Manjunath. I'm an associate professor in the Department of Chemistry, RV College of Engineering, Bangalore. So welcome back to my discussion about the various topics of chemistry of smart materials and devices. So in this recording, I'll be discussing about superconducting materials, which is included in the Unit 4, that is quantum materials and smart sensing. This course has been introduced for the first year engineering students of computer science and allied branches and biotechnology programs. This is the syllabus that we have included under this unit. You can find the videos related to quantum materials, related to graphene oxide, carbon nanotubes, etc. in other videos, and conducting polymers about polyamine in another videos. And also, I've discussed about the electrochemical sensors, piezoelectrical sensors, and about the instrumentation. But in this recording, in this video, I'll be focusing only on the superconducting materials. We will discuss just briefly, not in depth. We will introduce you to the meaning of this and the Meissner effect, BCS theory, Cooper pair, and we explain the superconducting behavior of yttrium, barium, copper oxide, and some applications, and also the types of superconductors, type 1 and type 2. So superconductors are actually the materials you can see here. When you place a magnet on them at very low temperature, liquid nitrogen temperature, you can see that this is the liquid nitrogen and this is superconducting material. You can say YBCO. The pellet and the magnet will levitate on the surface of the superconductors. Okay, so there will be a gap here. So the magnet starts levitating on the surface of YBCO. So this property of materials are called superconducting phenomena. Let us discuss what is the origin behind this for a material to exhibit this kind of property. Okay. The meaning of superconducting materials are these are the special class of materials that exhibit zero electrical resistance. Below a certain critical temperature. So it is labeled as TC. And this phenomenon of superconductivity was first discovered around in 1911. It's about 115 years old phenomena by Professor I.K. Kamerlingh-Onnes. Right? So during his low temperature experiments on mercury. So he is Professor Kamerlingh-Onnes, and you can see the graph of his the results. He was working on mercury at low temperature. He was studying about the behavior, the conductivity behavior of the metals like mercury metal at low temperature. He found that when the temperature is decreased to below 4.2 Kelvin, the resistance of that mercury material suddenly drops to zero. So the resistance of the material suddenly drops to zero. So then he has done extensive research on this phenomena, and he introduced this superconducting material. So in the superconducting state, okay, the electrical current can flow without any energy loss. So that is at zero resistance. So making these materials highly efficient. So these superconductors also exhibit a unique, not only the electrical property, zero resistance, they also exhibit very unique magnetic behavior. It is also known as Meissner effect. I'll explain in the next slide. So where magnetic fields are expelled from the material. So they're expelled out from the material. This is called Meissner effect. So the superconducting state exists for any material only below a specific critical parameters. Like the first one is the critical temperature below certain temperature, that is called TC, and below and certain magnetic field, that is critical magnetic field, and critical current density, GSE. So this is the graph representing the variation of the electrical resistivity with respect to metal, normal conductors, and with respect to superconductor. You can clearly see that the normal metal that is represented in the orange, the purple color. The resistance decreases, and it becomes almost constant, but it cannot be zero. So R is not equal to zero, even at very, very low temperature. Okay, there will be still some resistance even at very, very low temperature. But however, in case of superconducting materials, the resistance, it is represented the green line in the graph. In this graph, you can see that it is drastically decreasing the resistance. And when it reaches certain temperature, it suddenly drops. The resistance drops to zero. Suddenly it drops to zero. Okay. So that temperature is called critical temperature. So this is how we can differentiate the superconductors and the normal conductors. So let us look at the basic characteristics of the superconductors. The first one is zero electrical resistance. So these superconducting materials exhibit zero electrical resistance, means the electrical current flows without any energy loss. And the second one is the perfect diamagnetism. So this is another important property. Superconductors expel the magnetic fields from their interior. So this is called Meissner effect. You can see that the superconductors, the temperature is greater than Tc, they just behave as a normal conductors. Okay, you can see that the magnetic flux, it is just passing through the material, but when it is below certain temperature Tc, you can see that the magnetic field is expelled out from the material. Okay, they're not penetrating through that material, so that's why it becomes superconducting. So the next, they exhibit that property that is at below critical temperature. So this is the maximum temperature below which the superconductivity occurs. Then we have another characteristics features that is called critical magnetic field. So this is a maximum magnetic field the superconductors can withstand. Okay, so above that it loses its superconducting property. And similarly, the critical current density. This is the maximum current density uh, without destroying the superconductivity. So it's this superconductivity is a reversible phenomenon. Okay. So lost when temperature, the magnetic field or current exceeds these critical values. So if it crosses TC, HC, and JC, this material loses its superconducting behavior. Let us understand the Meissner effect. So this is the one which explains why the superconductor is different than the normal conductors. What is this Meissner effect? The Meissner effect is the complete expulsion of the magnetic field lines, from a material when it becomes superconducting, that is at below Tc. You can see that. So this is the Meissner effect. Okay, so this is actually the Meissner effect. It is expelled out. All the magnetic flux is being expelled. So when a normal metal is cooled, it only reduces the resistance. Okay, only the resistivity decreases, but it does not exhibit any the magnetic property, the expulsion of the magnetic property. However, the superconductor, when they are cooled below Tc, they not only reduces the resistance to zero, they also actively pushes the magnetic fields out of its interior. So this is the special behavior of the superconductor. This causes a magnet to levitate above the superconductor. So Meissner effect proves that the superconductivity is not just zero resistance. It is also the resistivity and as well as the magnetic property. It shows the superconductors are also the perfect diamagnets. So because of that, they expel the magnetic flux from their interior. So therefore, they're responsible for this is the responsible for magnetic levitation and stable floating of magnets. So next, let us understand the Lenz law. So Lenz law explains why the superconductors exhibit the perfect diamagnetism, so that we observed in Meissner effect. Okay, so Lenz law states that the induced current always opposes the change in magnetic flux that produces it. Okay, in normal conductors, the induced current oppose the magnetic field changes temporarily. Okay, that is in normal conductors. And in normal conductor, resistance causes the energy loss. As a result, the current decays. So this Lenz law cannot explain the permanent magnetic field expulsion. Okay. So it suggests that the induced current can oppose only the magnetic fields. Okay. So therefore, the Lenz law is not alone is insufficient to explain the superconductivity. So let us understand this Lenz law in detail. So let us consider this figure in which you can see that the first one, this is the magnetic you can see that this is the north pole of the magnet and this is the south pole of the magnet. And this is the direction in which the magnet is moving. And we have a coil. So this is the coil. Okay. So the conducting coil. And you can see that when the current is induced in this direction, the current is induced in this direction. This is the right hand thumb rule. When the current is induced in this direction, in this coil, this is the direction of the current, right? This is the direction of the current. It is induced in this direction. Then the magnetic field of the coil, the magnetic field of the coil will be in this direction. Okay. So this is as per the right hand thumb rule. Okay, right hand thumb rule. So when the current is induced in this direction, then the magnetic flux will be in this direction. So this is induced current and this is the magnetic flux. So when a north pole of the magnet, we having the magnetic field B mag. When approaching the coil, the magnetic flux through the coil increases. So here the magnetic flux of the coil increases. So the induced current produces a magnetic field opposing that increase. So when it moves towards that, the magnetic flux of this coil increases. Therefore, the induced current produces a magnetic field opposing that increase. So therefore, the coil nears the face. The coil nears the face. This side becomes a north pole. So therefore, north to north leads to repulsion. So this leads to repulsion. So this is what the Lenz law explains. Let us understand if you reverse the direction of the current, the induced current. If the induced current is in the opposite direction like this, according to Thumb's rule, the magnetic field direction changes in the opposite direction. Okay. When North Pole is moving away, when the North Pole is moving away from the coil, the magnetic flux through the coil decreases. The magnetic flux, this decreases, the magnetic flux. So the induced current produces a magnetic field supporting the original field. So the coil face becomes south pole. So this becomes south pole and this becomes north pole. Then it starts attracting here. So it's exactly opposite behavior. When it increases, it tries to decrease. When the magnetic flux, magnetic field increases, the magnetic flux is decreased by that coil. Then when the south pole, in both the cases, the north pole is approaching here and it is moving back. When the south pole is approaching, the third case, towards the coil, the magnetic flux of the coil increases in the opposite direction. Okay. So it is in the opposite direction. It increases. The magnetic flux increases. The induced current I produces the magnetic field opposing that change. So whatever that increase will be compensated by the induced magnetic field by the induced current. So therefore, the coil nears the face. So this becomes south pole. So south, it starts repulsion. So this is what the Lenz law. So this diagram demonstrates the Lenz law, where the induced current in a coil produces the magnetic field. The induced current in a coil produces a magnetic field that opposes the change in the magnetic flux caused by the moving magnet. So here the moving magnet changes the magnetic flux of the coil. If it try to increase that magnetic flux, the induced current try to compensate that increase by decreasing, by changing the direction, and vice versa. So that Lenz law explains only the temporary flux opposition, so increase or decrease. So that is not sufficient to understand the superconducting behavior. Okay. So therefore, we need the theory that is called BCS theory, which explains the permanent flux expulsion through the Cooper pair supercurrents. So let us understand the Cooper pair meaning first. Cooper pair is a pair of electrons that bind together at a very, very low temperature in a superconductor. You can see here, this is the superconducting material, and we have two electrons here, electron 1 and electron 2. They are bind together in the superconducting material. This pairing occurs due to attractive interaction mediated by this lattice vibration. You can see that this is the lattice vibration. These are the lattice, they starts vibrating. So that lattice vibrations results into the phonons. Okay. So that phonons is actually the quantized form of that vibration. Each quantum of lattice vibrational energy is called phonons. So this is a quantized form. So that electrons in a Cooper pair have the opposite spin. You can see that it is the spin is in the direction is opposite to this. This is above and this is below, and also the momentum is also opposite. So that is in the moment. These are the characteristics of the Cooper pair. So Cooper pairs move through the crystal lattice without scattering. So zero scattering. They move within the lattice. So resulting in zero electrical resistance. So this is the reason why we get zero resistance in superconductors, because the Cooper pair moves without scattering. So there is no energy loss in this. All Cooper pair acts coherently as a single quantum state. So all Cooper pairs acts as a single quantum state, which is essential for a superconductivity. So this is about Cooper pair. Next, let us understand the BCS theory of superconductivity. So BCS theory was proposed in 1957 by Professor Barden and Professor Cooper and Professor Schaefer to explain the superconductivity. At a very low temperatures, electrons interact with lattice vibrations, that is called phonons, to form Cooper pair. So Cooper pair, as I explained, moves in the crystal lattice without scattering, leading to zero electrical resistance. So the BCS theory introduces an energy gap between a superconducting state and a normal state, preventing electron collisions. So the persistent supercurrents generated by that Cooper pairs cause complete magnetic flux expulsion. So that is the Meissner effect. So Meissner effect is because of the persistent supercurrents, which is actually generated by that the movement of the Cooper pair within that superconducting lattice. So this BCS theory explains the superconductivity as a result of Cooper pair formation through electron-phonon interaction, leading to zero electrical resistance and magnetic flux expulsion. So both are zero electrical resistance and magnetic flux expulsion. So let us understand the various, the two different types of superconductors, type 1 and type 2. So with respect to the various features, so superconductors with respect to the critical magnetic field, the type 1 superconductors exhibit single critical field, that is Hc. So superconductivity is destroyed abruptly above Hc. But in case of type 2, it will not destroyed completely, but it exists in another mixed form. It exhibits actually two critical fields, Hc1 and Hc2. Between Hc1 and Hc2, the superconducting material can also exist in the mixed state. So it means that the partial flux expulsion. So there is a partial flux, magnetic flux expulsion, or some part of the magnetic flux is penetrating through that material, not completely. That is the difference with respect to the magnetic field Hc, critical magnetic field Hc of type 1 and type 2. Next, with respect to the magnetic behavior, type 1 superconductors are perfect diamagnetism. So exhibit the perfect Meissner effect up to Hc. But type 2 superconductors, they exhibit partial Meissner effect. The magnetic flux penetrates as vortices in the mixed state. Then the superconducting transition. The type 1 superconductors, they have a sharp transition from superconducting to normal state. But type 2, they have a gradual transition through mixed state before becoming normal. They have a superconducting state, mixed state, and then normal state. The critical temperature for type 1 is very, very less, below less than, it's about less than 10 Kelvin. But type 2 superconductors can be relatively high, up to 133 Kelvin in cuprates. The examples for type 1 are mostly metals like lead, mercury, aluminum, or tin. For type 2, it is basically consisting of mixed compounds, alloys, and complex compounds like niobium, titanium, niobium, tin, YBCO, yttrium, barium, copper oxide, and defect containing yttrium, barium, cupric oxide, bismuth, strontium, calcium, copper oxide. So these are some of the superconducting materials. They exhibit type 2 superconductors. So with respect to applications, type 1 superconductors are limited because of its low temperature TC and low critical field. And type 2 superconductors widely used in magnets, MRI machines, maglev trains, that I'll be discussing in detail towards the end of this recording. And another two important characteristics of type 1, type 2 are they differ in penetration depth. Okay. So the penetration depth lambda is small for type 1 and it is large for type 2. What is meant by this penetration depth? It is actually the penetration depth is the characteristic distance from the surface of superconductor over which an external magnetic field decays exponentially to zero. So this is due to the Meissner effect. Okay. So then we have another characteristics that is called coherence length. So coherence length, it's actually basically it's an effective size of Cooper pair. It's a characteristic length or distance or length or distance. It's a distance over which the superconducting order parameter varies. It's very large for type 1 and it is very small for type 2. So it is a distance over which the superconductors remains uniform. For type 1, it is large. So therefore, the Cooper pairs are spread out. So therefore, and for type 2, the coherence length is very small. It means that the Cooper pairs are tightly bound. So tightly bound. So this is about the types of superconductors type 1 and type 2 and their comparison. You can clearly see that in this graph, both the type 1 and type 2 are clearly distinguished. This is type 2 and this is type 1. And you can see that this is the y-axis, the critical magnetic field, Hc, versus the critical temperature. And you can see that the type 1 can exist superconducting state between the critical field Hc and critical temperature Tc. So it exists in this superconducting state, the complete expulsion of the magnetic lens up to this Hc and up to this Tc. However, the type 2 superconductors, okay, so it exists in complete expulsion state up to Hc1. So Hc1, it is in this state, that is superconducting state, and Tc1. And after that, it enters into the mixed state. Mixed state means what? This is the mixed state, type 2. There are some part of that magnetic flux is still penetrating, and the partially it is expelling, not completely. So up to that is the magnetic field, the second critical magnetic field Hc2. So after that, it becomes normal state. So there is a Hc1 and Hc2 in type 2. After that, it becomes normal. So it enters from superconducting to mixed state, this one, and mixed state to normal state. So this is for Hc1 and this is for Hc2. So there are two critical magnetic fields for type 2. Let us understand the superconducting property of the yttrium barium cuprate. Okay, so this is high temperature superconductor. It's actually type 2 with a critical temperature Tc is about 92 Kelvin. It's above liquid nitrogen temperature. It possesses a layered perovskite crystal structures. This is the layered perovskite crystal structure. In this structure, the CuO2 planes, this one, are primary superconducting layers. So CuO2 planes are actually superconducting layers. So exhibit zero electrical resistance below Tc. This material shows a strong Meissner effect. It's a perfect diamagnetism. And the superconductivity is anisotropic, dominant along that CuO2 planes. The oxygen, that X, oxygen content controls the carrier concentration and the superconductivity. So that is, it also influences the extent of that Cooper field formation. So type 2 superconductor operates under high magnetic fields. So widely used in coated conductors, power cables, and magnets. Next, let us look at the role of each component of this structure. So towards superconducting behavior. So this structure is highly layered along the C-axis. Okay, it is layered. Okay, this is CuO2 layer, yttrium layer. We have a barium, it separates. Then we have a yttrium. So this is the black one is the yttrium layer, and the blue one is barium. CuO2 planes are the most important. These are the primary superconducting planes, as I explained. Okay, so that CuO chains acts as a charge reservoirs, supply the charge carriers, volts to the CuO2 planes. So the CuOx acts as a charge carriers to the CuO2 planes. So because of the oxidation defects, there will be a change in the oxidation state that has to be compensated by one metal, that is yttrium. Yttrium layer lies between the two CuO2 planes. It provides the structural stability and also it balances the oxidation state. Barium layers separate the CuO2 planes and CuOx chains. Yttrium is between the two CuO2 planes. So yttrium is between here, and barium is between CuOx and CuO2. So barium is between the CuO2 and CuOx. Yttrium is between the two CuO2 planes. Let us look at the role of CuO2. CuO2 planes are primary superconducting layers. The charge carriers move mainly with these planes, enabling the superconductivity. So strong electron correlation and Cooper field formation occur only in CuO2 planes. So superconductivity is highly anisotropic, which is dominant along CuO2 planes. Then the oxygen defects, that is oxygen vacancies, also play a vital role for the superconductivity of this material. The oxygen defects control the whole concentration in CuO2 planes. The proper oxygen content enables the optimal doping and high critical temperature. Oxygen vacancies disrupt the charge transfer and reduce the superconducting temperature, that is Tc. And very importantly, excess oxygen deficiency can destroy the superconductivity. We should be careful when we are optimizing the defects concentration. So, and then it becomes insulating material. Next, we have the yttrium, the layer. Yttrium, as I mentioned, it is located between the two CuO2 superconducting planes. It acts as a structural spacer and maintaining a proper layer separation of the two CuO2 because of that lattice vibration. It controls the interplane electronic coupling, contributing to anisotropic conductivity of that CuO2 planes. And very importantly, it provides the charge balance, yttrium 3+. It does not directly participate in superconductivity. It only supports to that CuO2 planes. Then we have barium, which is positioned between the two CuO2, between the CuO2 plane and CuOx chains. It holds apical oxygen atoms, forming a bridge between the planes and chains. So this facilitates volt transfer from the CuO chains to CuO2 planes. So this is essential for the formation of the Cooper pair and also for the superconductivity. It also provides the structural support and proper layer spacing. So overall, each component of this YBCO, yttrium, barium, copper oxide planes, COX, layers, chains, all of them are playing a vital role for the superconductivity of this material. So next, let us look at the applications of this superconducting material. It's widely used in power and energy. Lossless power cables, superconductors can carry electric current with zero resistance. No energy is wasted as a heat during transmission. So results in very high efficiency power grids, useful for future smart grids and data centers. Then it's used in fault current limiters. So automatically limit very high currents during the short circuits, protect transformers and electrical equipment, act instantly without electronics or software control. That is in power sector. Superconductor also playing a vital role in magnet technology, like in MRI machines, use strong superconducting magnets in MRIs used for the scanning the human body. Produce detailed images of the human body, widely used in medical diagnosis. Then it's also used in NMR spectroscopy. It uses superconducting magnets to study the molecular structures. This is the NMR spectrometer, important in chemistry, biology, and pharmaceuticals. Then it's widely used in maglev trains. Trains float above the track using this magnetic levitation. That is the bullet train concept that has been introduced based on this superconducting material. So no friction, very high speed and no low energy loss, smooth, silent and efficient transport. Then advanced research, it's used in particle accelerators, superconducting magnets control and guide the charged particle beams. Used fundamental physics research, helps to study atoms, particles and the universe. Then also used in electronics, like in superconducting quantum interference devices, that is called SQUIDs, extremely sensitive magnetic detectors, and it can detect very weak signals, even brain signals, used in medical imaging and research. So this is the SQUID. Then it's used in Josephson junctions. So the two separate two superconductors separated by a thin insulator. It's called topological insulators. Allow ultra fast and precise electronic switching used in high speed circuits and measurement standards. Then finally, it is used in the upcoming technology that is called quantum computing. So that is for superconducting qubits. So these are used as a basic units in quantum computers. Okay. So this is, you can see the 64 qubit machine and 256 qubit machine. So operate at very low temperature, enable much faster computation for complex problems. So important for AI, cryptography and future computing. So this is about the applications. So let me summarize about superconducting materials. Superconductors exhibit zero electrical resistance below TC, and we have discussed about the resistance and also the diamagnetism. They show perfect diamagnetism due to Meissner effect, which is the complete expulsion of the magnetic flux from the interior part of that material. We also understood the Lenz law, which explains only the temporal flux opposition. Then we introduced BCS theory, which explains the permanent flux expulsion. So that is based on the Cooper field formation. So then by taking YBCO, we have understood the role of each layers, CO2 layers, oxygen defects, role of yttrium, barium, which is responsible for the superconducting behavior. And we have also understood the type 1 and type 2 superconductors with respect to the various characteristic features, with respect to the magnetic field, critical magnetic field, with respect to the temperature, with respect to penetration depth, and also with respect to coherence length. So we have discussed. And at the end, we have discussed about their applications. So with this, I'll just stop my discussion. Hope you guys understood about these superconductors. So this is just a brief surface level discussion, just to design for the first year engineering students who study applied chemistry. as part of their computer science and allied branch courses. Thank you very much.